about the challenge. For those of you coming, already with calculus and these things, what differentiability is and this type of stuff. And the reference material also, and that I will share, will have a lot of things about differentiability if you need to review that. So I guess this part here, this challenge here, is a little bit more thing because what's your take on this, George? You think this is very the thing for, not for you obviously, but for some of the new entrants, like?
Yeah, I think it would help to be very, very familiar with vector spaces and at least a minimal understanding of a ring.
Yeah.
So I'm actually puzzling over the commutativity. I have to think about that.
Okay, well, that's the challenge. It's a tricky thing, well, I'm being cheeky to the thing, but yeah. You have to throw cheeky questions sometimes, even if it's obvious that the thing. Okay, so now let's go to again this notion. So I'm saying diffeomorphisms part 2 because we went through diffeomorphism part 1, which is the notion of diffeomorphism from one part of Rn to another part of Rn. The question is, can we define this notion just like we did with the notion of smooth maps, but at manifold level? And the answer is also yes, by doing it this way. So a map, so again, given two. Okay, so it doesn't have to be like, well, I've spoiled here. I didn't mean to put add this. I just meant to be to say let x and y be because of a theorem that will come after anyway. But let x and y be smooth manifolds. Okay, not necessarily of the thing of the same dimension, but you will see again the theorem will tell you that they have to be the same direction. So. Sorry for that. I didn't mean to put this here because it will become obvious. So a map F from X to Y is called diffeomorphism if the following holds. If F is a smooth map, it is invertible. Remember, a smooth map doesn't need to be invertible, okay? And most importantly, the inverse of it is also smooth, okay? When that happens, we say that the two manifolds are diffeomorphic. So we write this, and in I think I'm writing this here just to distinguish it from homeomorphism stuff. But in the literature, when it's understood, you are talking about smooth manifolds. You don't actually need to write this. It's already understood that you are talking about diffeomorphism. So we say the two manifolds are diffeomorphic. So just like homeomorphisms, we understand that when two manifolds are diffeomorphic, it means the two structures are essentially the same, okay? And it's also clear that diffeomorphisms are homeomorphisms, but homeomorphisms don't need to be diffeomorphisms, okay? And here's an example here that you can check with this. This map is a homeomorphism. However, it's not a diffeomorphism because the inverse of it is not smooth. Okay, so just the thing. And now it's also very interesting. It is possible for two manifolds to be two smooth manifolds to be homeomorphic at topological level, but then fail to be diffeomorphic. Yeah, this is very, very interesting. This is actually what will lead us to in a couple slides thing when we talk about exotic, the so-called exotic structures and these things. So this is very, very, very interesting. And obviously for, you can say it's also a little bit annoying, but this is one of the things that, bigger surprises that, topologies and differential geometers and these things found out as they started exploring these structures. we'll come back to it when we talk about exotic structures.
I have
yeah.
one question. By structure preserving, do you mean the atlas structure?
Yes, yes. So the thing, the smooth structure. This is what gives the thing defines the thing the manifold, right? So it means essentially when they are diffeomorphic, their corresponding smooth structures, are essentially equivalent. So there's no distinction to say. And here's a theorem. This is why I wasn't keen to write n-dimensional thing on the previous thing. So if you have an n-dimensional smooth manifold and a k-dimensional smooth manifold, then they are diffeomorphic if and only if the n equals to k. So that's the claim. So this means that this dimension of a smooth manifold is an invariant, right? Now, there's something very fascinating that it might be possible. So if you have an n-dimensional topological manifold, remember, smooth manifolds are built on top of a topological manifold, right? You add extra structure to it. So it might be possible. I hope different smooth structures such that, yeah, go ahead.
There's a question from Amir. Would you ever prove? Oh, you see it?
Yeah, I see it. Would you ever prove the diffeomorphism between two manifolds without knowing, or is it more about saying? Well, you will know by definition. By this theorem, you will know obviously the dimension that by default you have to know which the structure already telling you that you have to know which dimension that you are starting, even if you don't know the second where the map is going. By this theorem, if you know the dimension of the first manifold, let's say X, you will immediately know that wherever the map takes you, so that part that where your map lands you, that has to have the same dimension as the manifold X.
If I am allowed
you can
to
have,
give...
yes, that's true. Also, the second part of the question, you cannot have diffeomorphism between different manifolds of different dimensions. Yes.
If I can give a very broad hint,
yeah,
the diffeomorphism, the structure makes this proof much easier. It is very hard to prove for a general topological manifolds. So that's a big hint.
Yeah. So this is really very interesting, and we'll come back to this when we talk about the time when you see at this when we go through the notions of a smooth structure. You will see some surprises. Sorry, smooth exotic structures. And now here's a challenge. This one is a little bit simpler, but there are some cheeky questions there. That this is more of a the composition of diffeomorphism is between manifolds is also a diffeomorphism. Yeah, this one is like the identity. The identity map is also a diffeomorphism. And now these one you have to think a little bit. It's very hard to go on the fly. I hope.
I lost the slide. I don't see it.
Ah, okay. Has anyone else lost the slide? Okay, so Bob, thank you.
Let me refresh.
Right. No worries. Okay, I think we should just hang on. I promise we'll finish on the hour, so we can wait for our friend George to join us again.
My apologies.
Yeah, no, it's okay. You are back. I was just telling everyone that we will finish on the hour, so we can wait for you. Can you see the slides again?
Yeah, the slides are back now and the sound is back.
Yeah. So it's a very tricky challenge is whether a composition of, this composition, assuming that F1 is a homeomorphism and F2 is a diffeomorphism, whether the composition is a diffeomorphism and these things. And then the other way around is a cheeky question that nevertheless is good, especially for those of you who are struggling with these the notions between between these two notions. By practicing this type of thing, you kind of it becomes a little bit more. You solidify a bit your knowledge between the two. And there's more, actually, by the way, especially when we get to the diffeomorphism group section, which is right now here. Okay, so this set, diff of X, which is the set of all diffeomorphisms on X, this set actually is very interesting. Forgetting even the algebraic thing that's in here, this proposition, you can actually equip it with the topologicals, with the very rich structures like topological structure and this thing. We will do that in the next module, so there's no need to go through that to worry about that. But just giving you a hint that this is it has very rich structure that one can build on top of it. Okay, so the proposition here, for the time being, let's get into the algebra stuff. Let's stick with algebraic stuff. So the thing is, the claim is that this forms a group, and the identity is this. I guess this is already giving you one of the challenges before that. The ID is a diffeomorphism. Okay. And another thing, very interesting, there's a notion called homotopy type that this is again something that you don't need to know now. We don't need to discuss this because we don't have the language, the algebraic topology stuff, the homotopy theory stuff to talk about this. But we will definitely in the next module, talk about this notion of a homotopy type for the diffeomorphic group of a smooth manifold. And you will see in there are actually very interesting, hard to answer, especially for the cases of, like the four sphere, for example. Okay, in the case of four sphere, actually, you will see something very interesting about the four sphere. There's an open problem related to it. We'll come to that. So yeah, so this is a group, the group of diffeomorphisms of the smooth manifold. And here's a very interesting theorem. A very interesting theorem is that says if X and Y are two smooth manifolds, then their corresponding diffeomorphism groups are isomorphic in the algebraic sense, in the group theoretic sense. Okay, if and only if the two manifolds are diffeomorphic. Okay, this is a very interesting result. Okay, and now the question is whether the other way around is true. Actually, there's a challenge with this term for you. Whether if X is diffeomorphic to Y, if and only if their corresponding diffeomorphism groups are isomorphic. What's your hunch? I'll leave this as a thing that you can, as a discussion point. And here's a challenge. The first challenge is, the first one is, to try to, get a bit of intuition, by trying to think about the diffeomorphism groups of these concrete objects that you are all used to in a thing, just to just to bring something to give you some sort of a concrete type of for you to on your own to build some sort of intuition of what this guy does. We will cover exactly like the stuff that some of the stuff that this thing does, in terms of group actions and this type of stuff in the next module. But it's good for you to try to see what does this thing looks like for concrete examples, like in R3 or even Rn in general, or even for these guys, these like the sphere, for example, or circle and these things. And then have a cheeky question here also, especially for those who are struggling. This is a good thing for you because it definitely, for the rest, I apologize, my apologies. But yeah, so the claim is that obviously the group of homeomorphisms, homeomorphism also form a group, right? Because homeomorphism is also invertible, right? The composition 101 that you already went through. So the question is whether which of the inclusions here. This is for mostly for those guys who are struggling. For the advanced guys, I know this is you already know the answer and these things, So and then this one here is for the thing for you to scratch your head. Maybe some of you already know the answer to this, but whether the Filichev, I hope I'm pronouncing Filikiev, something like that, his name. I'm not sure how. Whether the theorem that this theorem here implies, or at least some sort of kind of give you some sort of thing that whether this is an algebraic invariant. So in other words, whether, just what I was saying, whether X is diffeomorphic to Y if and only if the two diffeomorphism groups are isomorphic in the algebraic sense, okay? So let's see. Now, before we go to the notion of a smooth exotic structure, I guess there's nothing. We'll come back to diffeomorphism groups in the next session, in the next module. So this is just a bit of a taste now that we are in what a smooth manifold is, But there isn't really much at this stage that I would like to ask you about it. Just try to go through these things, especially this. Now, a very natural question that we can ask, like I already hinted before in one of the slides, how many different smooth structures can we equip a given topological manifold? Okay. Okay, so George, you are having a problem with the slides?
Bob is now. I was just saying that I reset my browser and it's good now for me.
Okay, so maybe let's wait for Bob to see if Bob, can you still see the slides?
Okay, Bob is back.
Okay. Okay, so he can see the slides now. I don't see his message, so.
Yeah, he messaged that he can see the slides now.
Okay, yeah. So a natural question I was saying is that, how many different smooth structure can we equip? So by different, we mean non-equivalent smooth structures that we can equip a given n-dimensional manifold with. Now, this is very abstract. Let's make it a little bit more concrete in order to make life easier for us. So, for example, let's consider the smooth manifold to be Rn with the standard smooth structure, or in other words, the smooth structure given by the the standard atlas, that we covered a couple slides, a couple of sessions ago. So that's the use case one. The second one is for the n sphere, with the atlas given by the hue charts from the stereographic projection. I don't think I explicitly named this thing in I think some of the exercises, challenges that we went through, you probably, or even on the test book, you came across this this stereographic projection. So anyway, so when people talk about this question then, for our purposes, then can be rephrased like this. How many different smooth structures other than the standard ones are there for Rn and Sn? Okay, so these different, the different structures that exist for Rn and Sn that are different from these the standard ones, this is what people call exotic smooth structures. So when you hear people talk about exotic smooth structure, it means that smooth structures that are not equivalent to these standard smooth structures. Say, for example, in the case of N sphere or Rn, for instance. Okay, and here's a surprise. Let's start with the Rn. We could there are some things that we could have bunched them together, but I will do them separately to make it easy for you to digest. And I hope I didn't make anything in the wording of stuff to make you more confusing. So the good news is for Rn, for dimensions 1, 2, and 3, there are no smooth structures. Okay, so that's a good result. I think it was Roda, the result combination of Rado and Moisa and a few others that enabled this thing. Prove this. So up to diffeomorphism, there is only one smooth structure in these dimensions. Okay, so Barry was right in the thing a couple sessions ago when Barry was hinted, one when when we were talking about how many smooth structures. I think I remember Barry saying only one smooth structure. So you are right for dimension 1, 2, and 3. Okay, so that means that all the all smooth manifolds of dimension 1, 2, and 3 that have the underlying, that are built on the underlying standard topological manifold structures of R1, R2, and R3 are diffeomorphic to the structure given by the standard atlas. Okay, so that's a good thing. Okay. So another equivalent way to say that is that any topological manifold of dimension 1, 2, 3 that is homeomorphic to these as topological manifolds must be diffeomorphic to the smooth manifold generated by the thing. So that's another way of doing it. I hope the wording of this might be a bit ambiguous, but I hope you have a bit of a thing what this means. Now, for dimension greater than 4, there are no exotic structures. So up to diffeomorphisms, there is a unique smooth structure. So all the smooth structure generate the same type of manifolds. All the manifolds are diffeomorphic for dimensions greater than 4. Now, very interestingly, for dimension 4, this is not the case. It's like a disaster, more or less. What do you think is special about dimension 4? This is actually a good question that even mathematicians are trying to answer. The thing, we'll come back to this in a minute because I have some references for you to go and read. But surprisingly, there is an uncountable number of exotic structure that we can equip R4 with. This is amazing. Uncountable. Not even countable, uncountable. Okay, so this means that we can out of R4 we can build many uncountable number of smooth manifolds that are not diffeomorphic to the standard one. Okay, now for those of you, especially the physicists, I think we might. Okay, we don't have the physicists on the audience. I think we have Shiplu is a physicist. So for the physicists, our friends in physics, I guess we can ask this question. Which smooth structure on R4 is the right model for space-time? For instance, obviously there's more into it. It's there's other considerations when modeling space-time. Yeah.
Amir is asking, what do you think is special about dimension 4 that causes this?
Yeah, well, this is a golden thing. Nobody really, I don't think there is a general answer. Even mathematicians are scratching their head about this, whether it's a coincidence of nature or not. Yeah, but I don't know my answer. I don't know. I'm not sure if there's any general. There might be some high level like results that hint about the thing, but it's definitely a special. It's very very special situation. In fact, some of the references you can go a little bit more, saying, including some talks that I will give you, by people like John Milner and these type of people who are being responsible for discovering these exotic structures back in the 50s and these things. People who opened the Pandora box, I guess, before these guys started showing up all over the place. Milner in particular. So yeah, it's a good question, and the answer is I'm afraid I don't know. There might be some good hints on these things, but it's a very interesting question that in dimension 4, out of all the dimensions, you have this phenomena. Yeah, and this is for R4. We'll see in a minute for the N sphere. There are also something interesting. So for the N sphere, the same. For dimension less or equals to 3, there are no exotic structures. So similar to the case of that we see for R4. So up to diffeomorphisms, these guys have unique S1, S2, and S3 have unique smooth structures. Okay. Now, for dimension 4, again, as far as I know, this is an open problem whether the 4 sphere has a smooth structure. So this is called the smooth Poincare conjecture. So as far as I know, this is an open problem. I'm not really up to date with the latest research and these things in this thing for a few years now. But as far as I know, I think this is still an open problem. So, it seems like mathematicians are split. Sometimes someone publishes something and then stuff tilts to one way that yes, there might be. Other times, no, they're probably not. So yeah. So again, for dimension 4, it's very interesting that in this case there is an open problem whether there is any exotic structure. Now, for dimension greater or equals to 5. There might be or there might not be. If there's like it must be only finitely many exotic smooth structure on the thing. If there is, but it doesn't say how much exactly. It doesn't tell you. Yeah. Okay. So if there is only, at least it's not uncountable. So it's telling you that there is it's finitely many. Okay. So this is again people like Kerver and Milner. However, there are some results. I'm not sure if partial results is this thing, but at least for comfort, like for example, if I'm not mistaken, for dimension 7, there are 28 smooth structures for the 7th sphere. And very interestingly, for dimension between 5 and 61 and 61, the only N spheres that don't have smooth structure, if I'm not, maybe I hope I didn't forget to include any, is S5, S6, S12, and S61. Look at the randomness of this. Huh? You will see the reference. I'll give you the references for papers where these results. And just as a curiosity, I picked S15. It turns out S15 has 16,256, if I'm not mistaken, smooth structures. Now, just for those of you who are curious, how did they get to this number? Mathematicians like developers or DevOps guys, they are very efficient. They're not going to construct the stuff. They build tools tools to enable them to compute this. So they're not manually, going and building, 16,000 something, constructions. There are actually tools, a little bit advanced tools that enables them to actually count this. In fact, one of the references, you will see this on the thing, if for those who want to dive into these things. And it is also a conjecture that, so given this, that for n greater or equals to 5, indeed, the only n spheres without exotic spheres are these guys. So anything else, this conjecture is saying that must have an exotic structure. So this is an open problem. Yeah, you will see this in one of the references. So Amir is asking, what is the thing? does it give us that makes it interesting? Well, not being different, because those are like the standard. They are like the gold standards, essentially, you know, for doing all sort of stuff that you do. For example, calculus and this type of stuff, right? So if you don't, if these other guys are not diffeomorphic to them, is it complicates. It's very interesting from a mathematician's point of view to see these the existence of these creatures in a way. But for like if you are a physicist, or other people in the applied topic, you like doing calculus, you like doing all this stuff, these things, you might find these other guys a little bit more. You never know, some of these creatures might have like applicability in actual practice. And I believe some string theorists, they play with some of these exotic structures and these things. But but it's important. It's just not just in terms of classification. Also, mathematicians like to classify stuff, so that's why it's important that it is in terms of classification, that they pick something like they have some sort of a role model, if you will, and then try to classify which others are of the similar class, of the similar role model type of thing, if the analogy works. But it's interesting from even if they are not diffeomorphic to Rn or Sn, it still makes them very, from a mathematical point of view, to have these creatures that were only discovered, I think, in the late, it's not less than 100 years ago, I believe, or possibly just over. Yeah, so to answer to your question, I guess, is to say that it means that they are very, I guess the hint is on the name, exotic. They are very like creatures. Maybe George can help me find a word that I would put into these exotic structures to why they are like fascinating and these things. And they also keep mathematicians awake.
It's like it means the subject is still alive. We don't know everything about it.
Yeah.
That's what my perspective on it.
Yeah. I guess it's like you are a mathematician. Say, for example, Amir, you are an explorer, in the sea. You go to the ocean, you find a completely new species that has no precedent before, that's no close to any other species. So this is the same, I guess, similar type of stuff when you find a new species in nature that has no resemblance to the species that you already, know how to deal with. The wonder. Yeah. So I guess it's like aliens. It's like so these exotic structures are like finding aliens for mathematicians.
I think, not that I understand physics deeply, but that these structures are global structures. And in physics, I think you can really only look at a local part of space-time, that your telescopes only see so far. So
actually, this is very yeah, go ahead. Very interesting. Maybe I'm actually tempted to bring one of the physicists to give us a perspective on the thing. Maybe Shiplu, would you like to come in? He's a physicist. I can bring you on board just to comment on, if you are free, of course.
Yeah. But my comment means that this existence of exotic diffeomorphic structures is a consequence of the global topology. So the difference between the whole space Rn and the sphere Sn, the difference is topological. But what's mind-blowing is that this topological difference makes an even more radical difference in the possibility for these exotic diffeomorphic structures.
Yeah, I mean, it's a fascinating, and these things, and for people like working in these branches of theoretical and mathematical physics, like string theory and these things, that they touch a lot, the mathematical machinery on these objects and these type of stuff. It's very, very, very interesting.
I think what I was saying about physics, but I wait for a more knowledgeable physicist to comment, is that we really only examine an open ball. We don't really see any global structure. We can make hypotheses and guesses, but everything you do in physics, if I'm not misunderstanding, is within an open ball.
Any physicists want to comment on the thing yeah, actually, one of the things that I will do now, that maybe that's more suitable after we start Lie groups and these things, is to start inviting mathematical physicists and theoretical physicists, because then the reason I'm reluctant to do that right now is because we don't have the language in order to understand them when they come in to give their talk and this thing. But we are getting there. Once we go through Lie theory stuff and these things, you will be able to to follow. So it will be a thing to invite a physicist to, especially those who are working in gravity stuff, quantum gravity, this type of stuff. We should have the mathematical. Yeah. Okay. So he says, yes, physics depends a lot on local structure. We care more about local. Yeah. So I think you are happy that you only want to use the test and these things. I'm also happy to bring you on stage so you can comment. Actually, it's good to have the time, because George and I were both mathematicians, so it's good to have a physicist angle. Okay, so I'll bring you on thing. So let's have a physicist view on space time and all this stuff. Okay, so he's coming in. Give us some insights. Did I invite him? Hello.
Hello. Yeah. Can you hear me?
Yes, we can hear you. Enlighten us. Yeah.
Yeah. So I would not actually, comment much on the global properties, because it's actually this kind of stuff's actually mostly concerned for those physicists who work actually on gravity. But for other people, like let's say I work in nuclear physics, so it is excluding gravity. And in our cases, like the local properties is actually matter most. For example, Lie group structures. So whatever your smooth manifold is, like you have a local tangent space which is essentially flat, and that matters actually most in most of the cases. But global properties also have some importance. For example, even in classical electrodynamics, sometimes when you study the electrodynamical behavior, like I'm just talking about the pure classical electrodynamics without even gravity. So sometimes you say that the boundary properties, the conditions you impose on the boundaries, that's actually affect the mathematical structures you are talking about. The similar thing, it actually happens probably more exotically when you include gravity. But since this is not my area of study, I just studied probably taken two course, and it's been a while, so I will not actually make comment on how much that is effective in case of gravity. But particularly if you invite someone who works on mathematical physics, I mean, not just string theory, but for example, quantum field theory, but the mostly concerned with the mathematical structures, they can actually answer these questions more appropriately, I would say. Yeah. But from the application perspective, I think even it is actually probably sad and sometimes I would say silly that, for example, in the nuclear physics and in particularly I do applications of quantum field theory in my work, and even though these Lie group structures is pretty trivial, so essentially, as long as you know matrix Lie group, that is probably enough. But that's obviously not enough for mathematicians. So yeah, and is that kind of satisfactory answer for you guys? I'm not sure.
No, no, it's good to hear your perspective. By the way, I hope I'm still on because I can feel a bit of cut. Can you still hear me? I think George, I don't see you.
Okay, I hear you, but I don't see you.
Am I still on?
I can hear you, but I guess you have the video blanked. I just see a capital Z.
Yeah, I can see both of you.
Okay, can you hear me? Both. Okay. Yeah, we can see you all and also hear. Okay. Yeah, thank you. Yeah, so thank you, Shiplu, for giving us this insight. And going back, because I know we are almost on the hour, so I recommend for this thing of exotic structure that we were just talking about. This paper. Obviously, it's very heavy in algebraic topology and other stuff. So you'll probably, but at least you can read the abstract and you will gauge some stuff that these the main points of this thing. It's a very interesting article. And another one, this one is this is where that conjecture is the one that says between dimensions 5 and I mean, the one. This is where the conjecture that dimension greater or equals to 5, the only n spheres that don't have the smooth exotic structure are the ones, the examples that I was just sharing, which is these guys here: S5, S6, S12, and S61. And another thing is, I really encourage you to watch this very interesting, enlightening talk by John Milner. I believe he was the first person. By the way, am I on? Sorry to ask. We'll finish soon, I promise.
I see you again and the slides, and I hear you.
Yeah, am I on? Am I still on?
Yes.
Yeah, okay, good, thank you. Yeah, so I encourage you to watch this with John Milner. I think he was one of the first, or if not the first person to discover an example of an exotic sphere. In this case, so, I encourage you to watch this. Just put John Milner spheres. This was in 2011, I think, as part of the Abel Prize stuff that he was presenting. And also, I recommend this one. Why is the four-dimensional smooth Poincare conjecture is still open? This is also a very interesting talk. So I encourage you to watch this as supplementary stuff. In reality, for our purposes, you don't really need to worry about all this stuff. This was just some extra motivation, some extra thing, touch of discussion for most of you. I mean, for our purposes, you don't need to know about this because we won't be dealing with the exotic structures in a way. So, and for the reference materials, again, for the calculus, because as you can see, there's a lot of calculus now things. So, I recommend this one also. And then this one by George, this Spivak thing. I finally had time to, found the stuff to include it. I didn't forget this time. It seems to have both some thing on calculus, but also in the context of manifolds, it's very useful in a way. Maybe less abstract than these guys. So I would recommend you jumping from this to this, but also use this for practicality to practice this one, calculus of manifold by Spivak.
The Loring 2 also.
Yes, so Bob, thank you for correcting. John Milner constructed the first exotic sphere in 1956. Yes. Yeah.
The
Yeah.
Loring 2 book also
So
covers
this brings me
much of what
to
Spivak covers.
the final thing I want to talk about is I want to give certificates of attendance, for those who are being, attending the course. And in this case, all I need you to do is, to confirm that you have audited, not necessarily because I know most of you don't have time necessarily to be attending the live session all the time, but, provided you audited the stuff, the videos and these things, and, most importantly, you went through the manifold section and these things, audited the manifold section, I'll take this as a face value. I give you a PDF certificate, nothing, something like this is the thing. If it makes any difference, the reason I'm doing this is because some people were emailing, asking whether the thing, I was like, okay, we'll do this. But this is for attendance. And then for the completion, so there's difference between completion and attendance, for those who can prove they got, I mean, most of the guys online now, I'm pretty confident that you know what a smooth manifold is. So, for those of you now, if you message me on Discord and these things, I'm happy to give you the thing, the actual, the certification of completion. Okay. Because I know, you being, consistent, following the, and I'm confident that, you know what a smooth manifold is. That's all I need you to know. So for the rest, the thing, I would ideally like to kind of, you give something, some sort of evidence that, you know what a smooth manifold is, So I'm enlisting the help of our friend George, possibly maybe Bob, maybe Shipulu also can help if you want something for those who are submitting something to get. But yeah, it's just to get. I mean, for the guys, for all of you that I'm seeing now, who are alive and listening, I'm very confident to give you that. Unless you tell me that you're still struggling with, what a smooth manifold is. If you tell me that, I'll believe you for those who are online now. So yeah, I'm happy to give you the actual this certificate, this digital one via Credible. So yeah, so just ping me on the thing on Discord or something, or send me an email or something. I'm happy. For those of you right now, I'm happy to give you the stuff. Just confirm with me that my suspicion that you already know what a smooth manifold is. I'll give you this. Okay. For the rest who don't have the thing, it's a little bit more harder. So yeah. So that's what I want to say. If it makes difference anyway, if it doesn't make difference, so why not? Why bother? So yeah. So again, this session will be available again on YouTube for replay. I really encourage you to go and replay the section, especially the manifold section. There are a lot of things that we didn't cover. This brings me to the other thing that I want to say: the extra sessions. That I would like to take, so we can touch other stuff that we didn't touch. I think Shikru, for example, was talking about the tangent space, this type of stuff that we should touch, and some other people are interested in fiber bundles, this type of stuff. So, but I want to do it after we go through, because I promised to have a session on career related stuff. So I'll get that out of the way, and then hopefully before module 2, we can have these crash course optional for only for those who are interested. They want to go through the advanced stuff that we didn't cover for this crash course, because the objective of this crash course was just to know what a smooth manifold is. That's it. If you know what a smooth manifold is, that's it. The way the group structure and the manifold coexist together, this is something we'll do in the second module. Okay, so that's it. It's been a pleasure again to be on this journey with you, and yeah, I look forward to kind of seeing you again, and keep up with the newsletter. I will send up some announcement about the other activities, like the career stuff that our event that I will hold, and this type of stuff. And yeah, for those who the certificate stuff, please ping me. I will also send another follow-up email. So yeah. So George, you want to make any comment before we go? I know I don't want to take much of your time, guys.
I just wanted to say once again, thank you so much for this wonderful series. And Amir had to step off, but he also wants to thank
I
you.
think we
and
lost
he
George,
looks-
so that's fine. But about Shipulu, you want to make any comment, anything now that you're there?
That's interesting. I see you and hear you.
Okay.
But
I guess not,
anyway,
unless I'm
thank you
actually
so much.
off. I'm still on, right? Okay, yeah.
I
Okay,
see
cool.
you.
Okay, well, in that case, thank you so much, George, and everyone, for being part of this community and helping drive the discussion. Bob, Amir, everyone on the thing on the Discord. I really encourage you to join George on the thing on Fridays, whatever, where there is like a discussion and to go through the stuff. So yeah, I look forward to seeing you again, and keep up with the newsletter and the announcement and these things for what next. So well done, congratulations for completing the crash course. You are now ready to take on Lee groups. Okay, so George,
Thank
just
you.
a final thing. You don't want to say anything? I guess George is
Oh,
off, so that's fine.
I lost sound. What's...
Okay, in that case, okay, does anyone want to comment anything before we go? If not, well, have a good weekend, and I'll see you around. Thank you so much. Thank you, George. I know you are having connection issues. Okay, Bob, thank you as well. And thank you, everyone. Thank you, Claudia, Stefano, everyone. Good to see you guys. Okay, bye. Okay.